Okay, hello everyone. I'm Vandana. I'm a PhD candidate at the Center for Intelligent Sensing, advised by Professor Andrea Cavallaro from QMUL University and Dr. Alessio Bruti from FBK, Italy. So today I'll be presenting our work on ConflictNET, end-to-end learning for speech-based conflict intensity estimation. So first I'll present the problem statement, then I'll go into the ConflictNet architecture, and finally the results. So let's begin with the definition of verbal conflict. So it is defined as an open and interactional dispute between parties or people who pursue incompatible or conflicting goals, and each party perceives that their interests are being opposed or negatively affected by another party. So in most simple terms, verbal conflict means conversational disputes. So the goal here is to measure the level or the intensity of a verbal conflict. So the question is, can we assign a single numerical value to a given duration of speech that indicates the perceived level of verbal conflict? And this task was first introduced in Interspeech 2013 Computational Paralinguistics Challenge. A little bit more details into the architecture. So in the previous session, the speaker said about end-to-end convolution, end-to-end networks. So ConflictNet is an end-to-end convolutional recurrent neural network architecture, and it is equipped with an attention mechanism. So by end-to-end, we mean that it is a single stream DNN architecture, and it takes raw speech signals, time domain signals as input, and it provides a single numeric value as output, and it is trained in an end-to-end fashion. So we have used 6 different types of layers here, namely convolution, max pooling, average pooling, LSTM, attention, and fully connected. So I'll go into a little bit detail about the choice of different architecture components. So since we are using raw speech signals, we have used one-dimensional convolution layers, and we have used 3 of them. And as the network becomes deeper, we have increased the number of convolution filters and progressively decreased the filter sizes. This is because of the fact that with
Vandana, you have been muted. Vandana, can you hear me?
It said the host unmuted me, muted me. Hello?
Yes, please, you can continue.
Oh, okay. This is because of the fact that with increased depth, the network learns more detailed features. And after each convolution layer, we have done batch normalization to reduce internal covariate shift effect and to increase the speed up the training. So we found that instead of using convolution with strides, it is better to use max pooling layers to downsample the output and to reduce the number of network parameters. And the pooling size of the max pooling layer was determined by the following equation, which takes into account the filter size of the previous convolution layer as well. So this is a common formula which is found in speech emotion recognition literature. Next, we used LSTMs to capture the interdependencies of features across time. In our experiments, we found that restricting the number of time steps to lesser than 250 gives better performance. So for that purpose, we have used a temporal average pooling layer before the LSTM. And to focus more on the portions of signal which are more relevant for the conflict, we have used a self-attention mechanism between the 2 LSTM layers. And finally, to obtain the conflict intensity value, we have used a dense layer with linearly activated single neuron. So this is the entire ConflictNet architecture. And since it is end-to-end trained, and the primary metric that we are using for evaluation is Pearson correlation coefficient. So the loss function is a function of correlation coefficient, that is 1 minus correlation coefficient, because we want it to increase. And the data set used is the same as the data set given in the interspeech challenge, which is SSPNet conflict corpus. It is a data set consisting of televised political debates where there is a lot of conflicts. And we have used, apart from PCC, we have used both weighted and unweighted average recall metrics as well. So we have compared our method with 10 different methods from the literature. And we have found that our end-to-end method performs as good as the state-of-the-art method, which is reference number 9 here. So our method gives 0.853 PCC, whereas the state-of-the-art method gives 0.856, which is a very slight difference. And in contrast to our method, the method 9 uses additional information and additional acoustic features, as well as it is not end-to-end. So it is interesting to see that an end-to-end model which takes pure raw speech signals with no additional information can perform as good as a network that uses different components and different acoustic handcrafted features. So this is the plot of ground truth values versus predicted values. And we can see that it has a good correlation, and it shows a correlation of 0.853. So for more details, you can refer to our paper, and I have put a code and a small demo in this link as well. So that's it. Thank you.